All right, let's see. Upcoming things. There is some homework due tonight, and there's homework due Wednesday nights. All of that is stuff from chapter 14, so you can already start working through that. Another upcoming science seminar if you're looking for your extra credits. There is one today at 3 o'clock in MAC 113, just over there. And then we're going to do one more individual quiz on Wednesday this week. So, yay. Okay, that was it. I have your quizzes to give back at the end of class today, too. So, don't let me forget. All right, so we left off and we did the pH of 1. And figured out the pOH and the concentration of hydroxides. We'll do the other half of the problem and then we'll move on to some other stuff. All right, so let's say we have a pH of 10.5. The same thing. I want to figure out the hydronium concentration and the hydroxide concentration. So it's probably easiest if you're given the pH to find the hydroxide, or the hydronium concentration first and the hydroxide concentration second, right? So solving it similar to this. What does that turn out to be? All right, so then how do I go about figuring out the OH concentration? Right, the pOH is probably the easiest thing to do. So if I know pH, and that's 10.50, how do I go about figuring out what the pOH is? Yeah. All right, so if they both add up to 14, if I know one is 10.5, the other one has to be whatever's left. And then we can solve it just like we did this one. All right, how do we feel about that? Good? Good little math warm-up? Okay. So, you may be thinking, right, the last chapter we did was all equilibrium stuff. So how does acids and bases have anything to do with those big Ks? Well, let's talk about that. Equilibrium constants and their relationship to acids and bases. We'll come back to all this stuff over here. All right, so let's say I have an acid reaction. So I have an acid and water in equilibrium with their products. What would be one of the possible products from this reaction? All right, so if this is the acid, this is the base. All right, so if that's the acid, that's the base. What would be the acid on the product side? H3O plus. So then what is left to be my base? Right, A minus, which is the base. Okay, so then let's say I want to write the equilibrium constant equation for this reaction. What goes on the numerator for these, the products or the reactants? All right, products go on top. So we have this. So then these guys go on the bottom. What is the simplification we make? I don't include the water, right, because it's the pure liquid. So we just assume that to be 1. So now I have the products over the reactants of an acid equation. And I'm going to give this a specific name. Big K with the little a, which means that this is an equilibrium constant for an acid reaction. So it's the equilibrium constant as long as the acid is the reactant. And because of that, it's going to measure the strength of the acid. And by strength, I mean how likely it is to completely dissociate. Right, the stronger the acid, it won't stay together. Like HCl is a really, really strong acid. Always break up the H and the Cl. So if we think about that as an example, let's say my acid is now all right, so I have hydrochloric acid dissociating into the hydronium and the chloride ion. If I wrote out its equilibrium acid equation, right, I would have that. How much of the HCl is left after this reaction has reached equilibrium? Is there really any? Is there a lot, a little? Does this reaction mostly go to products or mostly come back to reactants? Right, mostly goes to products. And so this number is actually incredibly tiny. It's almost 0. Almost. And so we can think about, that's all just true facts. These ionization constants, these Ka's, measure the extent of the ionization. And so if I've got a K that is greater than 1, it means that it mostly makes products. It ionizes extensively. All right, so I have a gigantic numerator over a very tiny denominator. So K has to be greater than 1. Or I can have K less than 1. Which means I've mostly kept my reactants. It doesn't ionize very much. Which means my denominator is very large. My numerator is really small, so my K is less than 1. So if you have a K greater than 1, it means you have a strong acid or a strong base as a reactant. So a strong acid or a strong base is one of the things reacting. If you have a K less than 1, it means you have a weak acid or a weak base as a reactant. So we can use these equilibrium constants to tell us about what sort of acid or base is reacting and how much product we can expect to make. So that's true for acids. We can also make the same argument for bases. Where if this is my generic base equation, alright, so now I have a base and an acid. So B is the base, water is acting as the acid in this case. If it's the base, does it want a proton or does it have another proton to give away? Right, bases want the proton, which means that will be one product. So this base has abstracted one proton from water. What does the water have left? All right, all that's left is OH minus. Which should be a dead giveaway that that's a base and this is an acid. So let's do the same thing, but now we'll write an equilibrium constant with the small letter b, where b tells me I'm talking about bases. So does the numerator does the products go in the numerator or the denominator? Okay. All right, so let's now think through our two options, right? We could have KB greater than 1, or we could have KB less than 1. If I have KB that is, greater than 1, which is the bigger component of my fraction, the numerator or the denominator? Right, so the numerator has to be big. So if the numerator is big, do I have more products or more reactants? More products. So is this a strong base or a weak base? It has to be a strong base, right? A strong base would make lots of products, which makes the numerator really big, which makes KB greater than 1. All right, so then let's think through the opposite case. If I have an equilibrium constant less than 1, if it's less than 1, what is the greater component, the numerator or the denominator? Right, the denominator. So if the denominator is the greater component, do I have a strong base or a weak base? I must have a weak base because it didn't dissociate very much. All right, what if I have an equilibrium constant, big K, equal to 1? What does that tell me about the concentrations of the numerator and the denominator? They're equal, okay? Right, equal concentrations. So we'll have to do something special in those cases to figure out those concentrations. We'll use an ice chart because those are awesome. Can I have an equilibrium constant equal to 0? Is there any way to have it equal to 0? What if I put a 0 on the denominator? Right? Your calculator gets super angry about that. Right? Super angry. It usually gives you the error message and kind of freaks out a little bit. What if I had, what's the likelihood of having a 0 in the numerator? That means there's no reaction, which means you can't have an equilibrium constant. So when you get your quizzes back and you guys circled that k equals 1 is the false case, you've just thought through why k equals 0 is the only thing that can't happen. So k is 1 is good, k greater than 1, k less than 1, all reasonable. You cannot have an equilibrium constant equal to 0. Mathematically, there's no way to make that happen unless you don't have a reaction, in which case you can't have equilibrium because you didn't have a reaction. So, good, good. All right, let's then, now this is a table out of your book. It is a lot of acids, bases, equilibrium constants. A lot of information on here. The way it's kind of laid out is, as you can see, right, we have the name over here, its formula, it's Ka, and its conjugate base, and the conjugate base Kb. There's a lot of information on here. I'm going to flip it over and tell you what you really need to know out of it. You need to know 6 strong acids. So these are going to be the 6 and the only 6 that we consider strong in this class. So hydrochloric, hydrobromic, hypochlorous, hydrogen iodide, nitric, and sulfuric acid. Those are going to be the 6 acids that are considered strong. And the other acid we'll just call weak. So if you know the 6 strongs and it's not one of those 6, it's a weak acid. And there's going to be 6 strong bases you need to know. And the same thing, there's 6 strong bases. If you have a base that's not one of these 6, it's automatically a weak base. The acids are a little trickier because they don't seem to have a good pattern. Like there's 3 of the halogens, and then there's these 3. These are pretty straightforward. It's the alkalis and the alkali metals, each with their OH components. Okay. So, oh yeah, question.
This is going back to the equilibrium constants for the acid and base.
Mm-hmm.
We ever have like when you have a K greater than 1 for an acid, does that mean that it's going to be a K greater than 1 for a base too?
If it's a strong acid, it will make a weak base.
Okay. So I guess, it's the same formula for both of those.
Mm-hmm.
So I guess if you find that it's a strong acid, being that the K is greater than 1,
Mm-hmm.
you automatically discern that it's going to be a strong base.
No, they have to be opposites.
Okay.
So like in this case, if I have a strong base that makes this conjugate acid, you've just told me because that's strong, it makes mostly products, which means it's very unlikely for it to reverse. And if it's not likely to go this way, it makes it weak.
But wouldn't H2O be a strong acid see what I'm saying?
Yeah, water has a K of 1 times 10 to the negative 7th, which is neither strong nor weak. It's both. It's in the middle. So you'll very rarely have a strong acid and a strong base reacting together.
Okay.
Right, you'll have a strong base and a weak acid, or a strong acid and a weak base.
Gotcha.
If you have two strong things acting together, you'll make two other products over here. Yeah, okay. Okay, so, in fact, that, in like one slide, we're going to work through the math of how that's true. All right, so in order to compare acid and base strengths, right, so here we have all these Kas on a variety of sliding scale, but they're all pretty small. We're going to do the same thing we did with pH. Right, it's very hard to compare numbers when it's like to the negative 6 compared to the positive 6, trying to figure out which one is strong and weak. So we're going to use pKa values. So just like in pH, right, bless you. pKa is the negative log of the equilibrium acid constant. So, for example, let's say I have these three weak acids. All right, so I have three acids, all of which are in the same approximate range of acid equilibrium constant. Which one of these is the strongest based on the Ka? Formic. How do you know it's formic? Right, closest to 1. So formic is the strongest. Right? But it's a little hard to tell, all right, it's not as obvious as it would be if we had them as whole numbers. So let's go ahead and convert these to pKa's. So on our pH scale, when you're thinking about pHs, 7's neutral, right, on pH. How strong of an acid solution is it if you have a pH of 2? Right, very strong. Same thing here. The smaller the number, the stronger the acid. So hopefully that works together with pH, right? The smaller the number, the more acidic the solution. Smaller the number, stronger the acid. So as the pKa decreases, I have a stronger acid. So how can I then use this information to help me figure out things about acid strength, base strength, and overall reactions? So those are just the first 2 points are just recaps, right? As the Ka increases, you have a stronger acid, you get closer to 1, or even above 1. Base strength increases as Kb increases. So let's look at a relationship between a conjugate acid-base pair. So here I have an acid dissociating, and I have a base making a base reaction. Right, just like we did in chapter 14, these each have equilibrium constants. Happens to be the first one happens to be a Ka, the second one's a Kb, right, because it's an acid reaction or a base reaction. If I want to figure out what the net reaction of these two reactions combining, what is one reactant in this reaction? Or let's do it easier. What's something that cancels out? B minus cancels out. Okay, what else cancels out? HB. Does anything else cancel out? No. Which means my net reaction must be right, so I have water dissociating into, in this case, a proton and a hydroxide. I now have two equilibrium constants. What do I do to those to figure out the net equilibrium? Do I add them, multiply them, divide them, multiply them? Okay. And so if water's dissociating, what's the special equilibrium constant we use for that guy? That guy, yeah. Yep, that guy. Right, the water equilibrium constant. So this is super useful. So kind of like we do with pH, we know that pH plus pOH is 14. I now have a relationship of Ka to Kb, which means if I know half the reaction, I can figure out the other half because Kw is a constant. Or if we mess around with some logs, that would also be true. So if we know the pKa, we can figure out the pKb because they have to add 14. So let's look at some examples and put this into practice. Let's see, do I have them on the next page? No. Make yourself a little space. I wrote really big on that previous page. All right, let's see here. Let's do this one. So let's say I have this reaction. I have acetic acid reacting with water to make the acetate ion and hydronium. And then I have a second reaction, that's the acetate ion combining with water to make acetic acid and hydroxide. I know the Ka of this equation, but I want to go about figuring out the Kb of the second reaction. So two parts, I guess. One, I want to find the net reaction. And then I want to figure out what is KB. See if I can get them all in there at the same time. There we go. So let's do the net reaction first. What is the reactant in my net reaction? We'll back up. What cancels out? Okay, that guy cancels out. And there's one other thing that cancels out. Yeah, the acetate ion, which leaves me with two waters. So what reaction is that? My net, right? It's just the water dissociation reaction. So what is the equilibrium constant for that? 14th, but yeah, overall 14. All right, so if I know KW and I know KA, how do I go about figuring out KB? And that's it. Everybody get the same answer as me? Of those who have a calculator out? Okay, good. All right. Any questions about that? That's pretty straightforward, I think. Ka times Kb is Kw. So if you know one, you always know Kw. You find whatever's left. Okay. Because I could do another example. Do another example. Move on. Do another example. I'll do one real quick. We'll do this. Let's say I have, because I happen to have another example off the top of my head. All right, let's say I have NH4 reacting with water to make ammonia and hydronium. How is the NH4 plus acting? Is it an acid or a base? Okay, it's acting as an acid because it's donating a proton. So this is a base. If it's an acid, is this one of your strong acids? No, so it's a weak acid reaction. And water's acting as the base. So if I have a weak acid and water, is this an acid reaction or a base reaction? It has to be an acid because water is amphiphilic and doesn't really count. So this is going to be the Ka. So water is going to be in every single reaction. And it's going to act sometimes as the acid, sometimes as the base. And so you can't use it as your guidepost. The other giveaway should be that your product is this H3O+. If that's your product, it's definitely an acid reaction. All right, so the Ka for this reaction is 565 times 10 to the -10th. All right, so now we're going to look for the Kb, but we got to figure out what the Kb reaction is. All right, so if I already used NH4+ as the acid, what do I have to start off with to make this the base reaction? NH3. And is that one of your strong bases? No, it is a weak base. So we're going to weak base. There we go. Okay, and that's going to, again, react with water. So now if I know I have a weak base reacting with water, what is one product that has to be made? Yep, hydroxide, and then the NH4 plus. My aqueous are getting a little funky looking. There we go. And you know there's a base reaction because you made a hydroxide. That should be your other clue. 1, you have a weak base. 2, you made hydroxides. And if you make hydroxides, that's the point of a base reaction. All right, so again, we know Kw is 1.0 times 10 to the negative 14th. Typed it in too fast. That doesn't make any sense. All right, feeling more confident about those? A little bit better. We're at the next section, which is types of reactions. So we're going to look at specific types of reactions, predict their reactants, and then talk about their equilibrium constants. All right, so there's going to be 3 types of reactions we're going to look at. A strong acid reacting with a strong base, a strong acid with a weak base, a weak acid with a strong base. Those are going to be the 3 we look at. So the strong and strong reacting together is the easiest one to talk about, so we're going to start with that guy. All right, what do we know about strong acids and their ability to ionize? Completely, incompletely. Right? These are going to completely dissociate. But strong bases, complete or incomplete? Right? Those also complete. So if they both completely dissociate, we'll expect nothing of them in the, they will be all used up. There won't be any of the reactants left. So if I say, for example, let's see here, what's a good example? Oh, this one. We'll do this one. So I have hydrochloric acid reacting with sodium hydroxide. Is hydrochloric one of our strong acids?
Yes.
Sodium hydroxide, one of our strong bases. All right. So if they're both going to completely dissociate, what should one of the products be? Okay. All right, so if I used up a sodium and I used up a chlorine, the only thing left is a water. We'll do a few more and see if we see a trend. You will. You'll be ready for it. You probably already know what the trend is because we definitely covered this last semester. But in case you have forgotten for some reason, let's do... You notice the direction of arrows I'm using? Right, before it was the double arrows because there's a chance we could come back and make reactants again. Purposely going only one way because there's 0 chance that they're going to reform their strong acids or bases. So just arrows are only going one way. All right, so let's say I have nitric acid and potassium hydroxide. What is one product that will be made? Okay. Potassium nitrate. And what's left? All right, so in both these cases, I had strong acids. Reacting with a strong base. And both of them made water, right? Water. And a salt. So every time you have a strong acid with a strong base, you'll make a salt and pure water again. So unlike some of these other reactions we saw on these previous pages, so like over here, right, acetic acid waters one of the reactants and it makes a hydronium, or acetate ion reacts with water to make a hydroxide. You don't make pure, the only way you make pure water is if you have strong and strong. Yes, Stephanie?
What if the strong base is like CaOH2?
Then we have to rebalance it. We can do that. Let's see what color scheme is I using. So CaOH2. And let's see, which acid should I use with that? We'll just use this one. It makes a really funky looking salt because it can only donate one hydroxide at a time. So it's going to do this first and then it'll react with another hydrochloric acid. All right, how do I feel about that? Good? Good at making that prediction? All right, I'm going to stop there so I can pass out the quizzes. But we'll pick up with